Good morning. This is Dr. B. Geetawani. Today's topic is Turing machine in formal languages and automata theory. Turing machine is a model which was introduced by Alan Turing in 1936. And Turing machine is the mathematical model for the computer. Turing machine models the computing capabilities of the general purpose computer. Out of all the formal automata missions, Turing machine is said to be the highest capability mission. The basic model of the Turing machine will have a finite control, an input tape that is divided into finite number of cells, and a tape header that scans one cell of the tape at a time. The tape has leftmost cell that is closed at the left end and is infinite to the right end. If you take the diagrammatic representation of the Turing machine, there will be a tape which is closed at the left end and is divided into number of cells and it is infinite towards the right direction. Each and every cell can hold one symbol. This is said to be the input string. And after the input string is over, all the remaining infinite cells of the tape are filled by means of a special symbol known as the blank B. By the symbol B, all the remaining cells will be filled. So whatever be the given input string, that will be placed onto the input tape from the leftmost end onwards, and remaining cells of the tape will be filled by means of the symbol B. There will be a finite control. The finite control will be holding all the states of the Turing machine, and there will be a header pointing to a particular cell of the tape. That means the finite control being in a particular state, it is reading the symbol A3 now. So in one move, the Turing machine, depending upon the symbol scanned by the tape header and the state of the finite control, will changes the state, prints a symbol on the tape cell scanned, replacing what was written there, and moves its header towards the left side or towards the right side one cell. So this is the speciality of the Turing machine. When compared to the push-down automata or finite automata, we will have the transitions there. We will have the movements over the input symbols of the tape, but the header won't move towards the left side or towards the right side. Only one side of movement is possible in the PDA as well as in the finite automata. But in the case of the Turing machine, the machine can move either towards the left cell or towards the right side after the movement is completed. Now let us see the formal definition of the Turing machine. Formally or mathematically, the Turing machine is defined as m is equal to q sigma tau delta q naught b f. There are 7 tuples in the mathematical description: q sigma tau delta q naught b f, where q is the finite set of states present in the machine. Finite set of states. Sigma is the input alphabet from which input strings will be formed, and this will be a subset to the tau. Next, tau is said to be the finite set of tape symbols. It is also known as the tape alphabet, and compulsory a symbol blank B will be present in the tau, and this blank symbol B won't be there in the sigma. Please remember, sigma is the input alphabet. It will be a subset to the tau, but blank, the B symbol won't be there in the sigma. Tau is said to be the tape alphabet. So whatever be the symbols that can be placed in the tape, that all the symbols will constitute the tau. And sigma will be the subset to the tau. Compulsory in the tau, B symbol will be there. Q naught is the initial state of the mission from which transitions will occur. P is said to be the blank symbol, and B belongs to tau. F is the set of final states, and F is a subset or equal to Q. Delta is the transition mapping function which maps from Q cross tau to Q cross tau cross L comma R. Means by taking a tape symbol, by reading the tape symbol, being in a particular state, in a transition or in a move, the mission will goes to the another state, will changes the tape symbol by means of the another symbol, and the input header will move either towards the left side or towards the right side, one cell. Now let us see the instantaneous description of the Turing mission. Instantaneous description. The instantaneous description ID will give the status of the Turing mission at any instant of time. And the general format of the instantaneous description is alpha 1, Q, alpha 2. Here Q is the current state of the mission. Alpha 1 and alpha 2 are the strings of the tau. That means alpha 1 and alpha 2 are the tape strings, tape symbol strings. Suppose the tape is like this: A1, A2, A3, A4, 5, 6, so on. Presently the mission is in the suppose Q4 state, and the mission is reading the symbol A3. Now according to the description, the instantaneous ID of the current status can be written as A1, A2, the state Q4, next A3, A4, A5, A6. This is said to be the ID of this situation, of this status. So A1 and A2 are already processed. Currently the mission is in the Q4 state and the header is about to read the A3 symbol. So the A3 symbol have to be to the right side of the Q4 in the ID, and all other remaining tape symbols have to be written as it is. So A1, A2, Q4, A3, A4, A5, A6 is the ID. Now suppose the mission is in the Q4 state and it is about to read the A5 symbol. Then the ID will be A1, A2, A3, A4, Q4, A5, A6, blank. If you want, you can write the blank. This is the ID of this situation. I suppose you understood how to write the ID. Alpha 1 will represent the substring of the tape which is towards the left of the header, and alpha 2 represents the substring of the tape symbols which is towards the right side of the header, including the symbol that have to be read. Now let us define the move. Suppose the ID is like this: x1, x2, x3 dot dot dot, xi minus 1, q, xi, xn. Suppose this is the current ID of the mission. That means the mission in the tape x1, x2, x3, so on up to xn. This is the string that have been placed on the tape of the Turing mission, and the mission is currently in the Q state. It has to read the xi symbol currently. The tape header is pointing towards the xi. So this is the ID corresponding to that situation. Now suppose if there is a transition like this, delta of q xi is equal to p y l. What is the meaning of this transition? Means being in the state q, reading the symbol xi, the Turing machine is moving to the state p and replacing the xi symbol by means of the y and moving the header towards the left side direction. So pictorially will be like this: x1, x2, x3, xi minus 1, xi, xi plus 1, xn, next blank. All these strings are placed over the tape like this. And the finite control, the machine is currently in the Q state. It is pointing towards the xi. That means it has to process the symbol xi now. After the transition is over, the machine will goes to the state P and the header has to move towards the left side. That means in the next ID, the symbol that has to be processed is xi minus 1. So in terms of the IDs, the movement can be written like this: x1, x2, so on, xi minus 1, q, xi, so on, xn. On the transition, it moves to x1, x2, xi minus 2. The state has been changed to the p state and the symbol that has to be read now, how to be towards the right side of the state. So xi minus 1 will comes to the right of the p. Next, the xi is changed to the symbol y and the remaining symbols have to be written as it is, xm. So this is the movement corresponding to this transition. If delta of q xi is equal to p by l, in terms of the IDs, this can be represented like the move here. Next, suppose if delta of q xi is equal to p y r, means being in the state q, reading the symbol xi, the machine is changing to the state p and replacing the xi symbol by means of the y and moving towards the right side. Then the movement will be like this. In terms of the IDs, the move can be represented as x1, x2, xi minus 1, q, xi, so on, xn will move to x1, x2, so on, xi minus 1. Xi is changed to y. So we will write y here and the state have been changed to the p. So we will write the state p and the symbol that have to be processed next will be the xi plus 1. So xi plus 1 and the remaining symbols of the string will be kept as it is. So this is the resulting ID. Now let us see the definition of languages accepted by the Turing machine. When a string is said to be accepted means from the initial ID, if it goes to the final state, then the string is said to be accepted. That means from the being in the state q naught, which is the initial state, if the input string that is placed over the tape on certain number of moves, if they are leading to the ID like this, alpha 1 p alpha 2, where alpha 1 and alpha 2 are the substrings of the tape string and p is the one of the final state, then we will say that the string w will be accepted by the Turing machine. So the language accepted by the Turing machine is mathematically defined as set of all the strings w such that w is in sigma star and q naught w on certain number of moves, it is going to the alpha 1 p alpha 2 for some p in f. F means set of final states and alpha 1 alpha 2 are in tau star. That means they belongs to the tape alphabet. So this is the definition of the language accepted by the Turing machine. Generally, the class of the languages that are accepted by the Turing machine are known as recursively enumerable languages. Recursively enumerable languages. This is the highest category of the formal languages, also known as the type 0 languages. Type 0 languages. Now let us design a Turing machine and see how to construct a Turing machine for the given recursively enumerable language. Let us take the language as L is equal to 0 power n, 1 power n, where n is greater than or equal to 1. Let us design the Turing machine. So initially the tape will consist of some string which is taken from the given language. That means some number of zeros followed by equal number of ones. Say 3 zeros, 3 ones. Remaining all symbols will be filled with the blank. Some string taken from the given language will be placed. Okay. Now let us think of the logic. Repeatedly, first m reaches the 0, then replace this 0 by means of the symbol x and move over all the symbols until 1 is encountered, leftmost 1 is encountered. So when this 1 is encountered, this will replace by means of the y symbol, indicating the matching of the previous 0 that have been read. Now after changing the 1 to the y, move back over the y's as well as the zeros until x is encountered and move one cell towards the right side direction. Then we will get the 0 again. This 0 will also be changed to the x. Move again towards the right over the zeros and y's until 1 is read. So when 1 is read by the machine, that 1 will be changed to the y. Again same process. Move towards the left over the y's and the zeros until x is encountered. Rightmost x is encountered. Then we will move one cell towards the right side. If 0 is encountered, change it to x. Same process 1. So while moving towards the left, after x is encountered, when you read the cell that have been to the right of the x symbol, instead of 0, if y is encountered, then we can say that the first half of the string is completed. That means all the zeros are completely processed. Now we have to move towards the right side. If you move towards the right side over the all the y's, if you get a 1, it indicates that it is a wrong string. That means more number of ones are there rather than the zeros. If you encounter the blank symbol, then we can say that the string is in the correct format, equal number of zeros and ones are present in the string. So the machine will enter into a final state and the string will be accepted. So this is the logic of the Turing machine for this language. So now let us write the transitions for that one. M is equal to Q sigma tau delta Q naught P F. Here Q is equal to, for these transitions we need 5 states according to our logic. So I am naming them as Q0, Q1, Q2, Q3, Q4. I will explain why 5 these states and what is the role of each and every state. Next sigma is 0, 1 and tau is the sigma symbols and the symbols which we are using over the tape. That means we are converting the 0 to the x, 1 to the y. So x, y, and one more symbol, that is blank symbol, will also be there. So 0, 1, x, y, b constitute the tau. Next blank is blank only. And if I am making the last state, Q4 state as the final state. So f is equal to Q4. M is equal to Q sigma tau delta Q naught BF. Q is equal to, we need 5 states according to the logic which we have explained. So Q naught, Q1, Q2, Q3, Q4 constitute the set of states of the Turing machine. The input alphabet is nothing but the 0, 1, and the tape alphabet is 0, 1, the symbols which we are using for according to our logic, that is XY and also the B. So 0, 1, XY, B constitute the tape alphabet. Blank is blank only. F is equal to Q4. Now let us write the transitions. So for writing the transitions, I am using a table like this. Here the state, the tape symbol, 0, 1, X, Y, blank. So first initially the measure is in the state Q naught. So for the Q naught, we will get 0 as the first symbol to be read. So we will go to the Q1 and that 0 will be converted to the X and we will move one cell towards the right direction. So delta of Q naught 0 is equal to Q1 XR. There will be no movements over the 1 and X. Now let us go to the Q1 state. If you move towards the right, so I will write a example here at the bottom, keep track of the symbols. So here we are in the Q naught, this 0 have been changed to the X and we are moving to the Q1. So to the Q1, 0 is encountered. So what we have to do according to our logic, just we have to scan and move towards the right side direction only. So Q1 on 0 is Q1, that 0 is kept as 0 only and we will move towards the right, Q1 0R. So we will move all the zeros like that. We will scan all the zeros. Then we will encounter a 1. After getting the 1, we will change the state to the Q2 and that 1 will be changed to the Y and we will move towards the left direction according to our logic. This is for the case of the first round. In the second iteration, third iteration, if you move towards the right side direction being in the Q1, after the zeros are over, we may get Y symbol. So that Y symbol should also be just scanned and we have to proceed in the right direction only. So Q1 YR and there are no transitions over this. Next Q2. For the Q2, if you move towards the left direction, immediately we will get a Y. So Q2 YL. Next, if you move back, we will get the zeros. So Q2 0 L. Next, we will get the X symbol. Then if X is encountered, we will jump to the Q naught in order to repeat the cycle. So Q naught X and the movement is towards the right direction. Next, in the Q3 state, we have to move towards the right side and while moving towards the right, we will get the Y symbol, Q3 YR and blank symbol Q4 B, and here when you come to the Q naught will get Y symbol. So here we will goes to Q3 YR. And here Q4 is the final state. Once you enter into the final state, there will be no symbols that have to be processed except the blanks. So there will be no transitions over all the symbols. Q4 is the final state and the mission will halt here. There are no further movements from the final state. So this is the logic corresponding to the Turing mission for the language 0 power n, 1 power n. I will repeat the logic again. State Q naught, it is entered initially and prior to each replacement of the leftmost 0 by X. state Q1. We are using the state Q1 to search right, skipping all the zeros and y's until it finds the leftmost one. If the machine finds the 1, it will changes that 1 to y and enters the state Q2. Now in the Q2 we will search left for an x. We will scan over all the y's and zeros and will come to the x and enters into the state Q2 upon finding it, and we will move one cell towards the right to read the next 0. As the M searches right in the state Q1, if B or X is encountered before a 1, then the input is rejected. Why? Because too many zeros are there. So the input is not in the correct format. And state Q0 has another role also. If after the state Q2 finds the rightmost X, there is a Y immediately to its right, then all the zeros are exhausted. So from Q0, scanning the Y, state Q3 is entered to scan over all the Ys and checks that no ones remains. So after the Ys are completed, we will definitely get the blank symbol to the Q3. So Q3 over the blank symbol, it will enters into the Q4, that blank is kept as the blank only, and we will move one cell towards the right and the string is said to be accepted. After entering into the final state Q4, there are no further movements. So on 0, 1, X, Y, B, I kept dash. Why? Because all these movements are not possible, they are invalid. So this is the logic of this design. Now let us process a string for this logic. Take a string 0011. Let us represent the processing of the string by means of the IDs. So initial ID is Q0 0011. So Q0 on 0, where it is going to the Q1. So X Q1 011. Next X0 Q1 11. Next X Q2 0 Y1. Next it moves to Q2 X0 Y1. So Q2 on X, it is moving towards the right. So it is going to the state Q0. X Q0 0 Y1. X X Q1 Y1. On next move, X X Y. We are scanning just towards the right side. 1. On the next move, X X Q2 Y Y. X Q2 X Y Y. Now Q2 on reading X, it will jumps to the state Q0, and Q0 actually, if more number of zeros are there or still number of zeros are there in the given string, it will repeat the cycle. But now in the given string only 2 zeros are there and those 2 zeros have been converted to the X. So there are no more zeros left over. It is immediately getting the Y. So if it gets the Y, according to our logic, it has to enter into the state Q3. And Q3 has to process all the Y's. So here only one Y is there. So after the Y is read, the next symbol that is encountered for the Q3 is the blank symbol. Next, by reading the blank symbol, our Q3 will changes to the Q4 state and will move towards the left side and will stop. So the mission halts by entering into the final state Q4. So thus the given string 0011 is said to be correct and accepted by the Turing machine. So this is how we have to think of the logic and how to design the Turing machine for any recursively enumerable language. Now let us design another Turing machine for the language, L of m is equal to 1 power n, 2 power n, 3 power n, where n is greater than or equal to 1. That means strings should have the equal number of ones followed by equal number of twos followed by equal number of threes. We can use the same logic by reading the, let's take 3 ones, 3 twos, 3 threes. Let this is the given input string. After reading the 1, we will convert into x, we'll move towards the right. By reading the 2, we will change to the y, and we will move towards the right side direction to read the 3. After 3 is processed, it will be changed to the z. Then we will go to the left side direction over the 2's, over the y's, and over the 1's until x is encountered. After the x is encountered, then we will move one cell to the right side direction to read the next one. And we will enter into the initial state to repeat the cycle again. So being in the x, then this will be y, this will be z. Again come back, this will be changed to the x, this will be changed to the y symbol, and this will be changed to z. Now come back over the z, over the y's until x is encountered. So after the x is, after we obtain the x, by moving one cell towards the right side direction, instead of 1, if you get the y means it indicates that the entire set of ones have been processed. Now we have to verify that all the set of 2's are also converted into the y's. After the y's are completed, immediately we have to get a z. Then it indicates that even the number of 2's are also correct. Next, we have to scan over all the jets to encounter the blank symbol. So immediately after the jets are over, if you get the blank symbol, then the string is said to be in the correct format and the mission will enters into the final state and the string is accepted by the mission. This is the logic. Let us write the transitions for this one. Directly I am writing the transitions. Here the state and the symbols are 1, 2, 3, x, y, z and blank. These are the tape symbols. And here the stack tau is 1, 2, 3, x, y, z, b, and the input alphabet sigma is 1, 2, 3. Now let us see the transitions. First, the mission will be in the state Q0. By reading the 1, we will go to the Q1 and we will change that 1 to the x and we will move towards the right. So Q01 is equal to Q1 XR. To the Q1, that 1 will be kept as it is and we will scan over that one. Next, if you get the Q2, that 2 will be changed to the y and we will move towards the right direction. Next, Q2. For the Q2, if you go towards the right, it will encounter the 2 symbol and just we have to scan that 2 symbol. So we will be in the Q2 state only. So the transition is Q2 to R. Next, we will get the 3 symbol, then change the state to the 3. That 3 symbol will be changed to the Z and we will move one cell towards the left side. Now, Q3 state. Q3, when we will move towards the left, we will encounter the Z symbol immediately. So, Q3 ZL. After you crosses the Z's, then you may get 2's. So, Q3 to L. So, after you crosses the 2's, you will get the Y's. So, Q3 YL. Just you are scanning all the symbols and moving towards the left side. Next, you will get the 1's. Then Q3 1L. So, you will repeat this process until X is encountered. So, when X is encountered, you will jump to the state Q0 to repeat the cycle. So, Q0 XR. Now, you will move towards the right side direction. So, to the Q0, if you read the X and move towards the right, you will get the Y symbol. So now we will go to the Q4 state, and that Y is kept as Y only, and we will move towards the right. We will process all the Ys. Being in the Q4 state, we will process all the Ys. We will scan just like that, and we will move towards the right side direction. Then you will get the Zs. So if Z is encountered, let us change the state to indicate that we have completed the Ys. So Q5 ZR. So to the Q5 you will get Zs only. So Q5 ZR. After all Zs are processed, then finally Q5 will encounter a blank symbol. So if blank is read by means of the mission being in the Q5 state, it indicates that the string is in the correct format and all the symbols have been changed to XYZ. So we will enter into the state Q6, make it as the final state since this is the lossless transition, and that blank will be kept as the blank only and move towards the right side direction. So Q6, this is the final state. There will be no movements from the final state. So keep all the blanks here. Remaining all combinations are invalid combinations. Keep the blanks in this table to represent that they are invalid combinations. There are no movements for this combination. So this is the list of transitions. And the mission description or definition for this language is the TM M is equal to Q sigma tau delta Q naught P F, where Q is equal to, here we need the states Q naught, Q1, Q2, Q3, Q4, Q5, Q6. Totally 7 states are required for this logic. So 7 states are there in the Q. Sigma for this one is 1, 2, 3. Tau is 1, 2, 3, X, Y, Z. Why? Because we are using the symbols X, Y, Z to replace the 1, 2, 3. Also the blank symbol. So this is the tau for this mission. And delta I have shown in the previous table, transition table. Q naught is the initial state. So Q naught only. Blank is blank only. And the set of final state, only one state is the final state, that is nothing but the Q6. So Q6 is the final state for this language. So L is equal to 1 power n, 2 power n, 3 power n is accepted by this Turing machine. So like this, if any recursively enumerable language is given, based on the syntax and the format of the language, think of the logic and design the Turing machine appropriately. Thank you.